Tonight's journey drifts to the glowing rings of SN 987A, the haunting afterimage of a star that once tore itself apart. Over the next few hours, calm narration will trace how those delicate halos formed, how they evolve, and how a single dying star quietly reshapes its galaxy across millions of years. If you enjoy falling asleep to slow science and deep space stories like this, please remember to like this video and subscribe to the channel so you never miss a night among the stars. At a modest distance in a nearby dwarf galaxy, a blue supergiant star reaches the quiet edge of its life and sits wrapped in a faint cocoon of gas. This simple fact that a massive star ends surrounded by its own shed material becomes the key to the luminous ring that later forms around the explosion site. The star's outer layers drift outward for tens of thousands of years, and the surrounding gas settles into a narrow band around its equator like a mist pressed into a belt around a spinning sphere. Closer in the hot core keeps fusing heavier elements in nested shells that resemble compact layers inside a slowly contracting onion. Each layer processes material and passes energy outward while gravity presses inward with relentless steadiness. For a long time, nothing dramatic appears to change in the surrounding gas, which hangs in place as a dim, invisible reminder of older winds. In that region, density is slightly higher along one great circle than everywhere else, and that subtle imbalance is enough to define the future ring. The moment of collapse arrives when the iron core can no longer support its own weight and yields in a sudden implosion. In less than a second, the central region shrinks to a compact object smaller than a city, and an outward shock begins to race through the remaining layers. The energy released is roughly the same as the sun would radiate over many billions of years, but delivered in a brief and concentrated burst. To anchor that scale, it is like concentrating the entire lifetime output of a bright household bulb into less than a heartbeat. Near the star matter is whipped and torn as the shock sweeps through, while farther out the previously quiet gas still floats in relative calm. The first wave to reach that distant band of material is not the heavy shock, but a front of intense light. Photons rush out at light speed and arrive long before any dense shell of debris. At the location of the future ring, this flash acts like a vast momentary lamp switched on inside the surrounding medium. Dust grains and atoms scatter the arriving energy and emit their own glow, turning the once invisible band into a delicate outline encircling the blast site. The gas itself is not yet strongly shocked, but it responds to the changing radiation field by heating, ionizing, and cooling in a new balance. From a wider perspective, the scene shifts from the cramped interior collapse to a bubble of light several light years across that brightens and fades over days and weeks. The inner band of denser material now stands out as a slender ellipse against more diffuse surroundings, even though its actual geometry is a nearly circular ring, tilted with respect to the line of sight. Small variations in thickness create knots and clumps, but at this early stage there remain only mild irregularities on an otherwise continuous structure. Light behaves as a tracer of both density and geometry, revealing features that matter alone would keep hidden in darkness. This early glow provides a first payoff in understanding the ring is not created by the explosion itself, but illuminated by it. The explosion instead acts as a high-energy backlight that sketches shapes laid down long before. There is a limit to intuition here because the distances involved are so large that even a narrow band of gas spans many times the size of the original star. It is difficult to picture a ring that is thinner in relative terms than a sheet of paper wrapped around a ball the size of a building. In reality, the ring's thickness compared with its radius is even more extreme, and the combined behavior of light and gas is needed to reveal its true three-dimensional shape. Within that constraint, the pattern of emitted radiation still marks the sharp inner edge where density peaks and energy builds a bright ridge. Over time, as the initial flash fades, the ring dims again and returns to a quieter state. Cooling gas settles into a new equilibrium, and its glow sinks into the background light of the host galaxy. The scene shifts once more from an object defined by intense transient light to a structure waiting in semi-darkness for the slower, heavier shock to arrive. The band remains in place like a narrow rim on an almost empty sphere, storing information about past winds, past rotation, and past stages of stellar burning inside the long-dead progenitor. In that quiet pause between the flash and the impact, the geometry of the ring, its smooth curvature and its slight asymmetries all stand ready to determine how the next phase of the remnant will unfold. From a far enough vantage within the host galaxy, the band appears as a thin, glowing ring, suspended in a larger, almost transparent bubble. The central debris cloud still hides inside a compact knot of expanding gas, while the ring outlines a preferred plane where material once flowed more easily. The contrast between the quiet, narrow band and the violent core offers a simple organizing picture amid complex physics. It is like seeing the ripple lines on a pond, long after the stone has sunk out of view, with the patterns on the surface preserving a history of the motion beneath. The ring encodes information about how fast the star once rotated, how its winds shifted with changing internal burning, and how long the outflows remained focused into that equatorial plane. These clues matter because they link a brief, brilliant death to a lifetime of slower processes that are otherwise difficult to reconstruct. In that sense, the glowing ring is both aftermath and archive, holding a record of the star's final stages while shaping every later step in the remnant's evolution that follows in the next phases. Before the explosion, the blue supergiant already holds the shape of its future rings inside its own structure and winds. Its core is massive, about 20 times the mass of the Sun. That single fact means one star carries the material of a small cluster packed into a single bright point in its host galaxy. In cross-section, the interior forms a stack of shells. Each layer burns a different fuel and sends energy outward. Hydrogen fuses in the outer zones. Helium burns in a deeper band. Heavier elements fuse even closer to the center in a compact hot region. The effect is like a set of glowing hollow spheres nested one inside another, and growing hotter toward the core. In that compact space, densities and temperatures climb to levels that ordinary intuition finds hard to picture. From the outside, the star still appears as a simple dot of light against its background. At the same time, the outer layers do not stay fixed. The star steadily sheds gas into space through winds that blow outward for hundreds of thousands of years. The flow is not the same in every direction. In that region, gas moves more easily along the equatorial plane than toward the poles. Over long times, the outflow does not fill a perfect bubble. Instead, it slowly builds a slightly thickened band around the star's waist. On larger scales, this band is the seed of the inner ring that later glows so clearly. Closer to the star, changes in the wind leave gentle boundaries in density and speed. A slow, dense outflow can be followed by a faster and thinner wind. The faster gas catches up and presses on the older material. Where this happens, a thin layer forms with a sharp transition in density and temperature across a narrow zone. This boundary wraps all the way around the star like a continuous ridge. It marks a preferred distance where later shocks will strike hardest and light will gather into a bright curve. Three main ideas link together here. Layered burning shapes the star from the inside out. Long-term mass loss carries processed material away. Equatorial enhancement quietly focuses some of that material into a preferred plane. Together, they turn an apparently simple star into a structured engine that sculpts its surroundings. The layered burning acts deep inside where matter is rearranged into heavier nuclei. The mass loss acts at intermediate distances, moving that matter outward in steady flows. The equatorial enhancement acts farther out, where gas slows and piles up into a denser band. The combined effect is easiest to imagine as a terraced hillside built over time by many small slides rather than one sudden collapse. Each phase of burning changes which elements feed the wind and how fast the gas escapes. When the core burns helium, the outer layers respond with one pattern of flow. When heavier elements dominate the center, the envelope responds with another pattern. These shifts leave marks in the density profile of the surrounding gas, even though no obvious structure appears yet. The space around the star remains mostly dark. A limit of observation enters here and sets a boundary on direct knowledge. At the distance of the host galaxy, individual streams of gas are far too small to separate. Light that leaves the star and its surroundings blends all the details into a single bright point with a faint halo. The delicate bands of enhanced density stay hidden inside that blur. Even if sensitivity were perfect, the finite sharpness of light as a carrier of information smooths tiny features into a soft glow. Only much later does the supernova blast wave move through this medium. As it travels with the first flash of light, hidden patterns step forward as sharp ring-ons and arcs. Inside the star, time flows quickly for the core and slowly for the outer envelope. The innermost burning stages may last only months or years. In the same span, gas that left the surface long ago has already drifted many light months outward. That contrast in time scales means that when collapse comes, the star ends its life inside a bubble built from its own earlier history. The inner ring traces gas that departed during a particular range of ages, not the entire lifetime of the star. Outside this band, other material continues outward in more diffuse halos. These halos later become the outer rings and extended lobes. A visual anchor helps fix the picture. Imagine a series of translucent shells blown from a single point. Each shell leaves at a slightly different speed and angle. Over long intervals, the shells intersect and thicken in some regions, especially along a single favoured plane. Where they overlap most strongly, a narrow, dense torus emerges and holds its shape. The rest of the space fills with thinner, gentler layers that fade with distance. The real star behaves in more complex ways, but the broad pattern holds. Structure concentrates near the equator. Material above and below spreads more smoothly. This configuration sets the initial condition for everything that follows the moment of core collapse. In that moment, the line between interior and exterior becomes crucial. Energy released in the core must push through the stacked burning shells and through the envelope. It then runs into the pre-shaped winds around the star. Those winds do not receive the blast in an even way. Instead, they channel and sculpt it. Interactions grow stronger where density is highest and expansion runs freer where matter is thin. The later brightening of the ring is therefore not an accident of geometry alone. It is the visible expression of a long span of quiet, structured outflow from a massive rotating star near the end of its life. The story of the remnant then moves outward into expanding debris and a growing bubble of shocked gas. Through that change, the underlying structure stays in place as a hidden framework. It keeps the ring sharply defined. Around it, the surrounding remnant grows and slowly blends into the wider gas of the host galaxy. After the core collapses and the first light fades, the heavier debris begins to shape the space carved out by earlier winds. The expanding blast wave is now the main sculptor of the remnant's three-dimensional form. Close to the ruined core, the shock front is almost spherical and pushes outward in all directions with similar strength. It carries hot plasma, newly formed elements, and magnetic fields all wrapped inside a thin, advancing shell. As it moves into the structured medium left by the star, this shell starts to deform and slow in some directions. In the equatorial plane, the wave soon meets the dense band of gas that will become the familiar glowing ring. At that boundary, the shock slows, compresses, and brightens. Above and below that plane where the gas is thinner, the wave travels farther and faster, stretching into broad lobes that extend away from the ring. The overall shape begins to resemble a glowing lantern that is gently pinched in the middle. The ring marks the narrow waist while the lobes swell like soft caps at the top and bottom. On small scales, the interface where the shock hits the band is not smooth. The dense gas is clumpy and layered, so the front reaches some point slightly earlier than others. Each knot presents a small obstacle that folds and wrinkles the advancing shell. In that region, shocked gas piles up into bright beads and short arcs along the inner edge of the band. Just beyond them, a thin layer forms where temperature and density jump sharply across a distance smaller than the size of a typical planetary orbit. This narrow sheet acts as the main radiating surface, converting kinetic energy into light across many wavelengths. The key concepts in this stage are the blast wave, the equatorial ring, and the polar lobes. A blast wave is a moving front where pressure, density, and temperature change suddenly. It behaves like an invisible wall of compressed gas sweeping through a medium. The equatorial ring is the dense band already in place, lying in the plane where earlier winds piled up. The lobes are inflated regions above and below that plane, where the wave can expand more freely into lower density gas. Together, they create a structure that is not just a flat ring, but a full three-dimensional hourglass-like shape drawn in light. From a vantage point far outside the host galaxy, this structure still shrinks to a tiny patch. The entire inner ring spans roughly 1 light-year, a distance that light needs 1 year to cross. In everyday terms, that is like stretching the space between the Sun and Earth more than 60,000 times. Yet in the context of the galaxy, this glowing ring and its lobes remain a small decoration in a much larger pattern of gas. The scale shift from local structure to galactic surroundings is enormous, and the mind tends to compress it down to a smaller picture than it really deserves. Inside the blast matter that once lay in neat shells now streams outward in tangled filaments. Some filaments reach the inner surface of the ring and strike it at shallow angles, feeding fine feather, like structures that extend along the inside edge. Others pass through lower density channels and continue into the lobes. In those regions, the shock front stays smoother and less corrugated, and the emission appears as wide, faint caps rather than sharp arcs. The lantern image remains helpful. The waist glows most strongly where dense gas resists the blast. The top and bottom glow more softly, where the wave inflates larger, thinner cushions of shocked material. A clear visual anchor appears when the structure is imagined from a side view. The ring becomes an ellipse surrounding the central debris cloud. Above and below it, rounded lobes arch outward, forming a gentle glowing outline that frames the explosion site. Darker zones separate ring and lobes, marking where density gradients shift and the shock changes speed. The entire pattern rotates in thought as a single connected volume, revealing that the ring is not an isolated object, but the narrowest part of a continuous flowing shape. There is an important limit of observation here set by the fact that only a two-dimensional projection of this three-dimensional structure reaches any distant telescope. Different viewing angles would show different apparent shapes. Some would emphasize the ring as a near-perfect circle. Others would stretch it into an oval and hide the lobes behind it. Light also blends along the line of sight. Bright features in front mask fainter ones behind and to the sides. Reconstruction therefore depends on models and indirect reasoning about how gas and shocks behave, not just direct imaging. Resolution further blurs small filaments into smoother sheets of light. The true complexity of folds, knots and boundaries remains partly hidden inside that blur. Even within these limits, the main pattern stands out. Where density is high, shocks slow and glow. Where density is low, shocks hurry and spread. In the equatorial plane, the ring holds the blast back and raises its temperature, so radiation piles up along the band. In polar regions, the same explosion energy must fill a larger volume of space, so brightness spreads out and becomes softer. As time flows from beacons and hours after the explosion to decades and centuries, the blast wave keeps moving outward. The ring thickens as more of it becomes engulfed by the shocked gas. The lobes continue inflating and start to interact with more distant clouds in the host galaxy. What began as a sharp difference between waist and caps slowly smooths into a more even shell. The lantern-like structure broadens and ages, but the memory of its narrow middle persists in the distribution of density and brightness. In the following stories, that memory continues to guide how energy is shared between the ring, the lobes, and the wider medium around the remnant. As the blast wave reaches the dense equatorial band, the inner ring starts to reveal its fine structure in slow, patient detail. This structure is not a smooth loop, but a crowded chain of clumps and gaps that turn a simple circle into a textured three-dimensional torus. Along the inside edge, density rises sharply over a short distance, so gas jumps from relatively thin surroundings into a compact layer with a clear boundary. This inner face becomes the main stage where shocks concentrate their energy and where light gathers into a narrow, luminous rim. Farther out, the ring thickens and blends into more diffuse gas, so brightness fades gradually rather than stopping at a hard outer wall. The result is a band that has a sharp inner edge and a softer outer gradient like a cloud with a bright core and a gentle halo. On smaller scales, the ring breaks into knots separated by darker intervals. Each knot is a region where gas piled up more strongly during the long pre-explosion winds. A typical bright knot spans about 1 light month across, which is comparable to stretching the distance between the Sun and Earth 30 times in a row. Within that span, density and pressure rise far above the surrounding medium. When the shock reaches such a knot, it slows and squeezes the gas, heating it to temperatures that make it shine in X-rays and visible light. In the spaces between knots, the shock moves a little faster and produces fainter emission, so the ring appears as a broken chain of bright islands in a dimmer band. The main concepts in this scene are clumping shock heating and radiative cooling. Clumping means that matter gathers into discrete dense pockets separated by lower density channels. Shock heating describes how gas is compressed and warmed when the blast front passes. Radiative cooling is the process by which that hot gas loses energy by emitting light. Together they turn kinetic energy from the expanding debris into a slowly evolving necklace of glowing patches. At the smallest level, this transformation happens in layers no thicker than the span of a planetary orbit, even though the ring itself wraps around a volume a light-year wide. A calm visual anchor forms when the ring is pictured as a quiet archipelago, suspended in darkness. Each bright knot becomes an island of light with its own shoreline and interior, while the dimmer stretches between them act like deep channels of shadow. The shock front moves across this archipelago, lighting each island in turn, as energy flows into dense gas and then leaks away as radiation. The islands do not move very far compared with the blast. Instead, the front sweeps over them and leaves behind a wake of cooling-enriched material. In that wake, heavier elements mixed into the gas create subtle layers in temperature and composition. These layers stack along the thickness of the ring like gentle bands of different colour in a polished stone. On larger scales, the entire archipelago orbits the wreckage of the star, in the sense that all knots share a common circular path around the centre. Yet on even larger galactic scales, this ring and all its islands collapse into a tiny unresolved speck. The shift from a light-month knot to a light-year ring to a full galaxy shows how easily structure disappears when distance grows. Intuition often compresses these steps into a single mental picture, but in reality, each level has its own distinct physics and timescale. There is a clear limit of observation in this part of the story. No distant eye can separate the inner and outer faces of a single knot or resolve the thin cooling layers that trail behind the shock. Even the best images blur many physical details into a single pixel-wide ridge. Light from the ring also overlaps along the line of sight, so some islands hide others that sit behind them. In that region, understanding must rely on models of how gas behaves under compression, combined with spectra that hint at temperature and composition. Direct imaging alone cannot show every fold boundary and gradient that shapes the ring from the inside. Despite these limits, certain physical signatures remain robust. The sharpness of the inner rim indicates a strong density jump at that radius. The contrast between knots and gaps reveals how irregular the wind-shaped medium truly is. The relative brightness of the ring compared with the lobes shows where the blast has done the most work on dense gas. Over time, as the shock continues to press on the ring, some knots begin to stretch and distort. Fingers of hot material push into them and draw out narrow tongues of gas that point away from the centre. These tongues mark paths where heated plasma leaks into lower density regions, softening the edges of the original clumps. Cooling then creates thin skins around these structures so they glow along their surfaces, while interiors grow darker. The archipelago slowly changes shape as islands erode and merge, yet the ring as a whole keeps its basic circular outline. On longer timescales of decades, the pattern of bright and faint regions evolves like slow-moving weather. Some knots brighten for several years and then fade as they lose energy. Others only start to glow later when the shock reaches slightly more distant clumps. The ring never flashes all at once. Instead, light travels around it in phases, giving the impression of a signal that walks along the inner boundary. At a given moment, one stretch may shine strongly, while another lies quiet. On the widest scale, this entire evolution is brief compared with the lifetime of the remnant. The period during which the inner ring appears as a sharp archipelago of islands lasts only a small fraction of the centuries-long expansion that follow. Eventually, shocks move beyond the ring and deposit their energy into more extended gas. The islands lose their brightness and blur into a thicker, more uniform shell. Yet even then, the memory of the ring persists in the density pattern that shapes later emission. The next stages of the remnant will build on this scaffold, turning a sharply defined torus into part of a larger, softer structure that gradually blends with the surrounding medium. Farther from the shattered core, two broader and fainter bands of gas wrap around the explosion site in a quiet geometry. These are the outer rings, gently curved shells that sit above and below the bright equatorial circle and complete a three-dimensional frame around the remnant. Each outer ring traces a region where older winds once flowed more easily along slanted paths rather than in the main equatorial plane. Instead of forming a tight torus, the gas in those flows settled into wide arcs, centered on the star but tilted with respect to the inner band. Their edges are less sharply defined, and their brightness is lower, yet they follow a coherent structure that extends well beyond the inner ring's narrow waist. A key detail is that the outer rings lie at greater distances, spanning a scale of about 5 light-years from end to end. That distance is comparable to stretching the gap between the Sun and Earth more than 300,000 times in a row. Across this vast domain, density gradients are smooth. The gas thickens gently toward the ring arcs and thins away from them. In that region there is no sudden jump as in the inner ring, but a gradual rise and fall in material like a soft ridge on an otherwise even landscape. The main concepts shaping this scene are latitude-dependent outflow, gentle density gradients, and extended curvature. Latitude-dependent outflow means that past winds favoured certain angles over others, sending more material into specific bands above and below the equator. Gentle density gradients describe how matter increases and decreases smoothly with position rather than piling into sharp layers. Extended curvature refers to the way the rings bend across large distances, while still following closed near circular paths around the centre. Together, these ideas explain how the outer rings can be broad, faint and stable, while still linked to the same dying star that built the inner torus. A calm visual anchor appears when the three rings are imagined as a set of pale hoops hanging in space. The inner hoop sits around the waist of the remnant. Above and below it, two larger hoops tilt slightly, so their edges cross the inner one at an angle. From some viewpoints, the three shapes merge into a figure that resembles a delicate frame around the central debris with open gaps where darkness leaks through. The hoops are not solid objects, but thin bands of gas whose brightness marks at places where density and temperature reach just the right combination for emission. In this picture, the outer rings act as the upper and lower rails of a wide ladder made of light, while the inner ring forms the narrow middle rung. On smaller scales, each outer ring also contains fine structure. Clumps and filaments drift along its arc, though they are less pronounced than in the dense inner band. The gas here experiences lower pressure and milder shocks, so features remain more diffuse. Light behaves as a soft tracer, rather than a hard boundary, turning the outer rings into hazy outlines instead of sharp edges. Over years and decades, these hazy outlines respond to the passing shock fronts and radiation pulses that move through the remnant. They brighten slightly when compressed or heated, then fade back as energy disperses. Compared with the quick, vivid response of the inner ring, their evolution is slower and more subdued. On larger scales, the three-ring system sits within an even bigger bubble of disturbed gas created by the original explosion. That bubble stretches several light-years or more, so the outer rings occupy only a portion of its full volume. The scale shift from the intricate pattern of hoops to the host galaxy is substantial. Each ring, though large compared with the original star, becomes a subtle marking inside one small patch of a spiral arm. Intuition tends to shrink or flatten this hierarchy, but the difference between the star-sized core, the ring-sized shell, and the galactic environment spans many orders of magnitude in distance and time. A limit of observation appears strongly in this part of the story, and sets clear constraints on what can be seen. The outer rings are faint, so their light must compete with emission from surrounding gas and from the galaxy itself. Their low surface brightness means that detection depends on long integrations and careful subtraction of background glow. Even then, the rings appear only as thin arcs because only the brightest segments rise above the noise. Resolution also limits the view, Small clumps within the outer rings blur together, masking finer internal patterns. Only the broad curvature and general orientation remain reliably visible, while internal layering and small-scale motion stay hidden. In that region, understanding relies on combining the observed arcs with models of how early winds behave and how shocks propagate through extended halos. Despite these limits, the outer rings provide a valuable payoff in understanding the past of the progenitor. Their positions and tilt carry information about how mass loss changed with latitude during earlier burning stages. If the equatorial band reflects one favoured flow pattern, the outer rings reflect another shifted in time and angle. Together, they act like multiple contour lines in a topographic map, each line marking a different height and history. By comparing their relative distances and shapes, it becomes possible to infer how fast gas moved, how long it flowed, and how the star's rotation and internal changes influenced its surroundings. Over longer periods, the outer rings will also play a role in shaping the final remnant. As the expanding shock reaches them more fully, they will absorb energy, form new shocks, and feed extended emission into the larger bubble. The hoops will gradually thicken and blur, blending with the rest of the disturbed medium. Their distinct outlines will fade, but the extra material they add to certain regions will continue to guide the remnant's growth. In this way, the quiet, faint outer rings stand as both record and participant, storing the memory of earlier winds, while helping to steer the later evolution of the glowing debris that once formed a single massive star. Long after the first sharp flashlight from the explosion continues to rewrite the appearance of the space around the rings. This delayed illumination forms light echoes, moving patterns that seem to glide across distant clouds, even though nothing solid travels at their apparent speed. When the initial burst leaves the broken star, it spreads in a growing sphere. Wherever this sphere touches dust and gas, it briefly turns those grains into tiny sources of scattered light. The effect is like a camera flash in a fog-filled valley, where distant ridges and pockets of haze brighten for a moment as the pulse washes over them. Near the remnant, the sphere reaches the inner cavity quickly, and then pushes outward into the wider environment. At each distance, it lights one thin layer of material and then passes on. Dust grains scatter some fraction of the light back toward the host galaxy, outlining the surfaces they inhabit. A light echo is the delayed reflection of a flash from distant material. It carries information about both the original burst and the shape of the cloud that reflects it. In that region around the remnant, dust does not lie in a neat shell. Instead, it forms sheets and clumps stretched over many light years. The main concepts here are scattering, delay, and geometry. Scattering means that dust grains redirect incoming light in many directions. Delay means that scattered light takes longer paths before it reaches any observer. Geometry links those paths to specific positions in three-dimensional space. Together, they turn the single instant of the explosion into a long, slow unfolding of illumination across the surrounding gas. A quiet visual anchor appears when the scene is imagined as a dark hillside forest at night. A bright flash occurs at one clearing. For a short moment, different slopes and tree lines light up in succession, not because the light moves slowly, but because it must travel different distances to reach each surface and then return. In the cosmic case, dust sheets far from the remnant brighten as the expanding light sphere intersects them. The apparent bright arcs move across those sheets as the intersection surface evolves with time. On small scales, each dust grain is no larger than a grain of smoke. On intermediate scales, these grains cluster into filaments that span like months or like years. The scale shift from the tiny particle to the vast sheet is extreme, yet the brightness of the echo depends on both levels at once, on how individual grains scatter and on how many grains lie in each illuminated slice. At a distance of about 1 light year from the remnant, the light pulse needs roughly 1 year to reach a dust sheet and another year to return. That timing is comparable to the span between 2 seasons in an orbit of a planet around its star. Closer dust responds sooner. More distant dust responds much later. As a result, the echo does not end with the fading of the original flash. Instead, it continues for years and even decades as the pulse reaches more remote regions. In that time, the pattern of brightening patches acts as a gentle moving outline of invisible structures. There is a clear limit of observation in this domain, governed by sensitivity and by angular resolution. Light echoes are faint compared with the original burst and with the ongoing glow of the inner ring. Their surface brightness can approach the level of background emission from the wider host galaxy. Detecting them depends on long exposures and careful comparison over time. Resolution also restricts how finely the moving patterns can be traced. Small variations in the dust distribution blur together, so only the largest arcs and patches stand out. A signal would still carry information about depth and shape, but much of that information remains locked in subtle contrast that lie below detection thresholds. Despite these limits, light echoes offer an important payoff. Because each illuminated patch corresponds to a specific time delay, it lies on a known three-dimensional surface relative to the explosion. By tracking echoes at different times, it becomes possible to map the distribution of dust around the remnant. This mapping is not perfect, but it reveals whether material concentrates in broad sheets, narrow filaments, or more diffuse halos. In this way, echoes act like gently sweeping search beams in a vast dark hall, revealing where walls and partitions stand. On longer timescales, the echo patterns fade as the energy of the initial flash spreads thinner over an ever greater sphere. The illuminated patches shrink in contrast and until they blend into the general glow of the region. Yet the record they leave behind in images and spectra continues to inform the story of the remnant. Combined with the geometry of the inner and outer rings, the echo maps show how far the influence of the progenitor extends into its host environment. Close in the rings carry information about dense, focused outflows. Farther out, the echoes trace more diffuse clouds shaped by older events in the dwarf galaxy. Together they connect the tiny collapsing core no larger than a city to a volume of space spanning many light years. As the script of the remnant unfolds from seconds and minutes to years and decades, light echoes mark one of its gentlest chapters. They do not add new energy to the gas, but quietly rearrange visibility, turning hidden structures into brief drifting silhouettes. In the stages that follow, heavier shocks and expanding debris will dominate again. Still, the memory of these slow-moving waves of illumination remains part of the full story of how a single stellar death reshapes both its immediate rings and the wider fabric of dust and gas that surrounds them. At a certain moment in the remnant's early decades, the expanding shock finally catches the densest clumps along the inner ring and begins to wake them one by one. The result is a slow, uneven ignition that turns a previously uniform band into a sequence of sharply defined bright spots around the circle. The shock front that drives this change is thin compared with the size of each clump. It advances as a compact layer in which density, pressure, and temperature jump across a distance smaller than the gap between major planets in a typical system. In that narrow layer, gas that once drifted in a cool diffuse state is squeezed heated and set glowing across a wide range of wavelengths. The first concept guiding this scene is the forward shock, the leading edge of the blast that plows into the ring material. A forward shock is a moving compression wave that pushes into previously undisturbed gas. It behaves like a concentrated wall of motion that transforms random drift into organized flow and heat. Where this wall meets each knot, it presses hardest on the densest regions and wraps around them like water wrapping around a boulder in a stream. The second concept is radiative cooling, the process by which hot compressed gas loses energy by emitting light. Radiative cooling lets the shocked clumps shine as they shed heat, then dim as they relax. The third concept is instability, small irregularities that grow when different layers slide past one another. These instabilities wrinkle the shock surface and seed fine filaments that trail away from each knot. A calm visual anchor forms when the inner ring is imagined as a long curved bridge in darkness with lamps attached along its span. At first, all lamps remain dark. As the shock reaches the bridge, the lamps switch on in slow succession instead of all at once. Bright patches appear strengthen, then settle, while others further along the curve remain quiet until the wave arrives. The bridge itself does not move far. Instead, the moving front sweeps along it and carries the progression of light. In the real structure, each lamp is a dense clump, and the wiring is refaced by the path of the shock as it runs around the ring. On the smallest scales, the shock thickness is tiny compared with the radius of a clump. Gas just ahead of the front is cool and relatively neutral. Just behind it, the same gas is compressed by roughly a factor of 4, similar to squeezing a soft cushion to a quarter of its original thickness. This compression raises the temperature to millions of degrees and strips electrons from atoms. The clump develops a thin, extremely hot skin where emission in high-energy bands originates. Deeper inside, the gas warms more gently and shines mainly at lower energies. The boundary between skin and interior is a physical detail that matters because it sets where different colours of light emerge and how quickly the clump can radiate away its heat. On larger scales, the entire ring fills with a moving pattern of bright and faint patches. At any given time, some clumps sit behind the shock and glow strongly. Others lie ahead of it and still wait in semi-darkness. From a vantage point within the host galaxy, the pattern appears as a string of unevenly spaced points along an oval. Over years, these points change brightness as each clump passes through its own sequence of heating and cooling. The apparent motion of brightening and fading carries information about both the speed of the shock and the structure of the ring. A limit of observation enters in two ways and shapes how this evolution can be inferred. First, the finite ability of light to carry spatial detail blurs the thin shock layer and combines the hot skin with the cooler interior of each clump into a single unresolved glow. The true separation between different temperature zones remains hidden inside that blur. Second, time resolution is limited by how often signals can record the light from the ring. Rapid changes on timescales shorter than those intervals may occur, but remain invisible as separate events. Instead, they merge into a smooth trend. In that region, understanding relies on comparing models of shock, heating and cooling with the observed patterns of brightness changes rather than on direct inspection of every layer. Even with these limits, the clumps reveal key aspects of the interaction. Where the ring is densest, knots brighten more strongly, and for longer periods because they store more gas to heat and cool. Where it is thinner, emission appears fainter and more transient. The sequence of turning on and fading out across the ring therefore acts as a diagnostic of density variations. It shows where the original equatorial band was thickest and where gaps allowed earlier winds to escape more freely. On yet larger scales, the energy deposited in the ring does not stay confined to the clumps. After the initial heating pressure builds and begins to drive secondary flows, hot gas streams away from the surfaces of the knots into lower density regions, creating narrow tendrils that point outward and inward along the ring. These tendrils gradually feed material into the larger volume of the remnant, helping to smooth contrasts over time. The curved bridge of lamps slowly loses its sharp individuality as its supports erode, and its surroundings fill with a more uniform glow. The timing of these processes links seconds and minutes from the original collapse to decades of subsequent evolution. The shock that now crawls across the ring began as a sudden impulse near the collapse core. It travelled outward, across distances measured in light months and light years before arriving at the equatorial band. Now, in the span of a human lifetime, it spends only part of that time transferring its energy into the clumps knot by knot. After that stage, it will continue beyond the ring and work on more extended gas. By then, the bridge-like pattern of bright points will be fading. In the next chapter of the remnant's life, other structures will take over as the most prominent shapes, but the memory of this slow, sequential ignition remains encoded in the rearranged density and in the mix of elements now stirred through the region around the former star. Deep inside, the growing bubble of debris patterns of freshly made elements begin to take shape. These patterns decide how the remnant will feed the surrounding galaxy with new material. During the collapse, light elements near the core fused into heavier nuclei in a burst of intense compression and heating. That brief phase forged oxygen, silicon, and iron group elements in quantities that far exceed anything produced in ordinary stellar burning. The explosion then hurled this processed matter outward in an uneven way, so that some regions carry more heavy elements than others. Instead of forming smooth shells, the ejecta break into plumes and fingers that stretch from the central cavity toward the expanding shock. The boundaries between these plumes and the surrounding gas are sharp in density and composition, like edges in a swirling liquid that has not yet fully mixed. Near the centre, the plumes are thick and tangled. Farther out, they thin into filaments that curve through the interior of the ring. A useful concept here is nucleosynthesis, the forging of new atomic nuclei from lighter ones. In the explosion nucleosynthesis, acts mainly in the dense hot core just before and during collapse. A second concept is mixing the process by which these newly forged elements spread and blend through the expanding gas. The third is stratification. The tendency of material with different densities and origins to remain layered even while it moves outward. Together, these ideas describe how the remnant can be both ordered and chaotic at once. On large scales, heavier elements tend to occupy inner regions, while lighter material crowds the outer layers. On smaller scales, fingers of heavy material punch outward into lighter gas, while pockets of lighter elements fall back into deeper zones. The result resembles a swirling interior that has not settled, with contrasting streams crossing and folding as the remnant grows. One concrete number captures the scale of this newly forged mass. The explosion spreads roughly an amount of heavy elements comparable to the mass of the Sun into its surroundings. In everyday terms, it is as if a solid sphere with the mass of the Sun were shattered into invisible dust and scattered across a bubble several light years wide. At first, this dust is not in the form of grains, but of hot ions and atoms moving in a rapidly expanding flow. Only later will some of it cool and condense. In the early decades, the important feature is where different elements cluster. Oxygen-rich filaments may trace one network of streams. Iron-rich material may trace another. Their paths weave through the interior volume like coloured streaks in a slowly unfolding plume of smoke. These streaks do not yet glow with the same brightness as the shocked ring, but they influence how energy moves and where future emission will arise. A calm visual anchor forms when the interior is imagined as a loaf of bread marbled with darker and lighter streaks. Each streak represents a plume rich in a particular element. As the loaf expands very slowly in all directions, the marbling stretches and thins, but never vanishes completely. In the real remnant, the bread is replaced by hot diffuse gas, and the streaks correspond to regions where the history of burning and ejection differ. Some areas carry the signature of oxygen shell burning. Others carry the mark of silicon and iron core processing. The marbling is three-dimensional, so any single view through the remnant combines many different layers of pattern into one projected image. Here a clear limit of observation appears. No distant measurement can follow individual plumes from core to ring in direct detail. The spatial resolution available at the distance of the host galaxy blends many filaments into each pixel-sized fragment of light. Spectra reveal the presence of certain elements and their speeds along the line of sight, but not the full three-dimensional paths they trace. In that region, understanding rests on a combination of observed lines and models of how instabilities grow in an exploding star. The instabilities act where heavier gas overlays lighter gas and gravity and motion pull them through each other. They carve the smooth layers into rising fingers and sinking gaps, much as cream poured into coffee breaks into curling streams instead of forming a perfect sheet. Despite these limitations, the marbled structure delivers a steady payoff in physical insight. The distribution of oxygen and other intermediate mass elements points back to how the progenitor burned in its final hours. The placement of iron-rich regions reveals how deeply the explosion reached into the former core. Where heavy elements appear at large radii, it suggests that plumes carried them outward rapidly. Where they remain concentrated nearer the centre, it suggests a more contained mixing. Over centuries, as the remnant thins and cools, these patterns will govern where new molecules form, where dust condenses, and which parts of the surrounding medium become most enriched. On the smallest scales, the story involves nuclei and individual collisions. Protons and neutrons combine under crushing pressure to form heavier cores. On intermediate scales, packets of gas collect into plumes and filaments. On the largest scales, the entire remnant spreads its newly forged inventory across a cavity many light years across. That gentle series of scale shifts links minute interior events that lasted less than a second to the slow enrichment of interstellar space that will continue for hundreds of thousands of years. In later stages, when the bright ring has faded and the shock has moved far beyond its current position, the marbled interior will have softened into a smoother mix. Yet traces of its structure will still linger in slight variations of composition and density. Those traces ensure that the long-term evolution of the remnant remains tied to the brief intense period in which a single massive star collapsed, forged new elements in its heart and sent them outward in plumes that now wind silently between the glowing inner ring and the wider, quieter gas of its host galaxy. In the very first second after collapse, the brightest part of the event does not appear as light at all. Most of the released energy leaves as an immense burst of neutrinos that slip almost unhindered through matter. For a brief moment, the shrinking core becomes a source of invisible radiation more powerful than an entire galaxy in that same heartbeat. The core itself is now a compact object only a few tens of kilometers across, smaller than a city, yet holding more mass than the Sun. Around this new center, the rest of the former star still churns and falls, caught between gravity pulling inward and shock-driven motion pushing outward. In that tight volume, conditions decide whether the compact object remains a neutron star or continues inward into a deeper gravitational well. A neutrino is a nearly massless particle that interacts only very weakly with ordinary matter. In practice, a neutrino can cross an entire planet with almost no chance of striking anything. During the core collapse, an enormous number of these particles pass through each cubic meter near the dying star in less than 1 second. The effect is like a storm of tiny transparent grains rushing through a solid wall as if it were only mist. Almost every grain passes through without leaving a trace, yet a small fraction does collide and transfers energy to the surrounding layers. That small fraction is still large compared with other energy channels. It helps lift material that would otherwise fall back and strengthens the stalled shock that tries to move outward through the star. The compact object at the center is a neutron star if collapse halts before an event horizon forms. A neutron star is a body in which matter is squeezed so tightly that individual atomic nuclei merge into a dense fluid of neutrons and a few protons. At this density, a piece the size of a small stone would outweigh a mountain. In the early seconds after birth, this object is extremely hot and wrapped in a thick mantle of infalling and rebounding gas. Neutrinos stream out from its interior in all directions, carrying away heat much faster than light can escape through the still opaque layers above. The surrounding matter responds to this hidden radiation field. Close to the core, neutrino heating pushes on the gas just behind the shock and helps it regain speed after an initial stall. Farther out, the effect weakens and the layers continue to move almost ballistically. At this stage, the shape of the explosion can gain slight asymmetries. In regions where heating is stronger, or where matter is less dense, the outward motion becomes easier. In regions where heating is weaker, or where material is heavier, the flow slows. These gentle differences seed later patterns in the debris and help decide which directions carry more heavy elements and which remain relatively empty. There is a clear limit of observation linked to this phase set by the way neutrinos pass almost unhindered through nearly everything. Light from the explosion comes from outer layers and from the later interaction with the rings and surrounding gas. It does not show the detailed thermal history of the core. Neutrinos, in contrast, emerge directly from the deepest regions, but they are extremely hard to register across interstellar distances. A signal would carry a precise imprint of temperature and density in the core, yet only a minute fraction of that flood reaches any distant location. Most understanding of this neutrino-driven phase, therefore, rests on models grounded in basic physics, guided by sparse direct indications rather than rich images. On scales just outside the compact object, some matter that failed to escape at first begins to fall back. This fallback gas crashes into the neutron star and releases additional energy as it decelerates and heats. Some of it may spread into an uneven envelope that rotates and channels outflows along preferred directions. These outflows are broad rather than needle-thin. They nudge certain regions of the debris into slightly higher speeds and leave other regions slower and denser. Over time, this subtle steering by the core shapes where filaments of heavy elements end up and how they thread through the interior below the ring. A calm visual anchor appears when this stage is imagined as a drum set at the center of a shallow lake. The drum sounds once with tremendous force, but the sound itself is silent to any distant ear. Instead, its energy launches ripples through the water. Most of the energy passes through the lake in a single pulse, yet close to the drum the surface moves more strongly and stays disturbed for longer. In the real event, the neutrino burst is the silent strike, the overlying gas is the lake, and the Enhanced motion near the core is the region where the shock recovers and begins its outward journey in earnest. Over minutes and hours, the neutrino flood eases as the compact object cools. The burst that once carried almost all of the energy becomes a faint background. The neutron star, if it survives, settles into a more stable state with strong gravity, rapid spin, and an intense magnetic field. On timescales of years and decades, the visible evolution of the remnant is then driven mainly by shocks mixing and the interaction of expanding debris with the inner ring and more distant gas. Yet the amount of energy those shocks carry and the arrangement of elements inside them are already fixed by the first seconds. In the later glow of the ring and the slow widening of the lobes, the imprint of that early invisible phase remains. The long story of the remnant's rings and filaments still echoes the moment when most of the energy left as a silent tide of particles crossing the forming structure and flowing on into the wider dwarf galaxy that surrounds this single transformed star. Over the following decades, the remnant shifts from violent rearrangement to slow redistribution of energy. In this calmer phase, the inner ring brightens, holds its glow, and then gradually fades as the strongest shocks pass through its densest knots. Each passing year increases the radius of the expanding shell by only a small fraction of a light month, a change modest on galactic scales, yet large compared with the original star. The scene changes from a near instantaneous detonation to a long measured breathing of light and heat. The guiding ideas now are energy transfer, deceleration, and cooling. Energy transfer describes how the kinetic power of the blast wave is converted into internal energy and radiation as it sweeps through the ring and surrounding gas. Deceleration means that the shock slows as it gathers more mass trading speed for a thicker shell of disturbed material. Cooling tracks. How this heated material then loses energy through light in high energy bands, visible emission, and radio waves. Together, these processes regulate how long the ring stays sharp and when it softens into a broader, gentler glow. Close to the inner rim, the forward shock has already crossed many clumps. A reverse shock now moves inward through the expanding ejector heating gas that was rushing outward faster than the swept-up shell. Between these two shocks lies a contact region where matter from the ring and matter from the former star mix. Instabilities fold this region into curls and fingers so that dense fragments from the ring break apart and sink inward while plumes rich in newly forged elements push outward. Over time, the simple boundary thickens into a tangled band with gradients in density, temperature, and composition layered across its width. A quiet visual anchor appears when this stage is imagined as a shallow glowing basin with a bright rim. At first, the rim of the basin stands sharp above a dim and nearly empty interior. As energy flows inward, hot gas wells up inside the basin, and cooler, denser fragments slide down from the rim toward the center. The edge still marks a clear boundary, but the bowl below fills with a softer, more even light. The inner ring has not vanished yet. It now shares attention with a growing interior that holds an increasing fraction of the remnant's energy. On larger scales, the whole structure reacts to this internal rearrangement. As the blast wave sweeps up more gas from the ring and the wider medium, its expansion slows. Speeds that once reached many thousands of kilometers each second fall to lower values over decades. At some point, the mass of swept-up material overtakes the mass of the original ejector. From then on, the remnant behaves less like a small packet of debris rushing through a prepared wind, and more like a classical expanding shell in a roughly uniform environment. The ring changes role from a hard wall to a dense section within a single thicker bubble. There is a clear limit of observation during this middle age. The brightest interactions near the time when the shock first strikes the ring are straightforward to record. Later, as the shell enlarges its surface, brightness drops and light spreads over a wider area. Small changes in intensity unfold over many years, so following them requires long sequences of careful measurements. Resolution also becomes a challenge. Fine curls and fingers in the mixing layer blur together, so only their combined effect on the overall shape can be seen. In that regime, understanding depends on stitching together many snapshots and comparing their slow evolution with models of decelerating cooling shells. Even with these limits, the overall energy budget stays conceptually simple. The explosion started with a fixed amount of energy. As time passes, more of that energy resides in the motion and heat of swept-up gas, and less in the original compact ejector. Radiation carries away only a small fraction, but it marks where energy is currently being spent. When the ring glows brightest, it shows that the blast is doing its hardest work at that radius. Later, when the ring fades and a larger, softer shell grows more prominent, it signals that the main work has moved outward into more diffuse regions. On small scales near individual knots, the change from sharp bright bead to faint ember happens over only a few years. Across the entire ring, the collective brightening and dimming span decades. On the scale of the full remnant, the change from a strongly ring-dominated shape to a more nearly spherical bubble unfolds over centuries. This nested set of timescales links the brief flash of core collapse to a long era of gentle restructuring. A fresh analogy can anchor this shift. Early in its life, the remnant behaves like a struck bell, producing a clear ringing tone when the shock first meets the dense equatorial band. With time, that tone softens into a steady hum, as vibrations spread through the whole body and into the surrounding air. In the remnant, the inner ring is the bell's rim. The expanding shell is the spreading vibration, and the ambient gas is the medium that eventually carries the energy away. The sharp ring of light slowly becomes a more diffuse halo, as energy leaks into every direction. Eventually, the remnant enters a stage where its appearance changes only slowly across human lifetimes. The inner ring remains visible but no longer dominates the scene. A thicker, almost spherical shell of shocked gas surrounds it, and the narrow waist becomes only a gentle variation in a much larger volume. From the wider view of the host dwarf galaxy, the remnant now resembles a modest bubble in a filament of interstellar gas. In the long chapters that follow this bubble, we'll keep enlarging and thinning until its edges merge with the background, but the calm breathing of energy and light in these decades sets the tone for that extended quiet dispersal. From a distance within the host dwarf galaxy, the remnant now appears almost settled into a stable shape. That apparent calm hides a precise record of how a single massive star lost mass, spun and burned in its last stages. The triple ring system, the inflated lobes and the marbled interior together, form a kind of structured archive written in gas and light. In that archive, each boundary gradient and patch of emission holds clues to a particular phase of the star's life. The inner ring marks a focused equatorial outflow. The outer rings trace older tilted winds. The lobes show where low-density paths once opened along higher latitudes. The interior plumes preserve how heavy elements were thrown outward and how deeply the explosion reached into the core. One guiding idea in this large view is that of a diagnostic remnant. A diagnostic remnant is an exploded star whose present-day structure reveals details of its past. In that sense, the three-dimensional shape acts like a long-exposure photograph of many thousands of years of outflows layered onto one another. Another guiding idea is evolutionary pathway. Different massive stars follow different pathways, and their remnants display different dominant features. Some leave ragged shells without clear rings. Others show broad filament crossing patterns instead of narrow bands. The ringed structure here marks one particular path among many. A calm visual anchor forms when this structure is imagined as a stained glass window suspended in space. The bright inner ring becomes the central circular panel. The outer rings form curved panes above and below it. The lobes and interior filaments wrap around as coloured mosaics behind and between the main arcs. From some angles, this window appears almost flat. From others, its three-dimensional depth becomes obvious with pieces sitting nearer or farther along the line of sight. Light behaves as both painter and backlight for this window, outlining its shapes and revealing which pieces are thick, thin, smooth, or fragmented. One approximate number anchors the timescale of this archival record. Only about 4 decades have passed since the initial explosion, a span similar to half of an average human lifetime. In that time, the remnant has grown to span several light-years distances that light itself needs several years to cross. The shift from a fraction of a second in the collapsing core to decades in the rings and lobes shows how a brief event can control a structure that evolves slowly. The diagnostic remnant idea becomes clearer when compared with other known examples. Some remnants display a nearly circular shell without inner rings, suggesting simpler or more symmetric mass loss. Others show strong jets or long narrow filaments indicating different explosion geometries, or strongly directed outflows. In this case, the coexistence of a sharp equatorial ring, tilted outer rings, and mild lobes suggests a star whose rotation and winds were neither perfectly symmetric nor dominated by narrow channels. Instead, they produced focused but broad flows that shaped matter into a pair of high-latitude bands and gentle polar expansions. There is a limit of observation that applies strongly at this comparative level. Only a small sample of nearby explosions displays enough detail for such structural comparisons. Many remnants lie too far away, sit behind thick curtains of dust, or have ages that smear out early features. Resolution and sensitivity constrain which rings, edges, and filaments can be seen. As a result, models must bridge between a few well-resolved cases and many partially resolved ones. Inference about pathways must therefore remain cautious. Still, the clear geometry in this system acts as a reference against which more fragmentary shapes elsewhere can be interpreted. On small scales close to the inner ring, the diagnostic power lies in the precise position and thickness of the band. Tiny shifts in radius correspond to changes in wind speed before collapse. The difference between knotty and smooth sections reflects how steady or intermittent mass loss was in specific directions. On intermediate scales that include the outer rings, the tilt and separation signal, how earlier outflows changed in latitude preference and density. On the largest scales that encompass the full bubble, the overall symmetry or asymmetry of the shell reflects how evenly the explosion distributed its energy. The stained glass picture helps here. Individual panes correspond to directions in which outflows were stronger or weaker. Junctions between panes mark boundaries between different wind phases. The way light now shines through and around these panes shows how the explosion illuminated and reshaped what the winds left behind. Another gentle payoff appears in the link between the remnant and the broader population of massive stars. In regions of ongoing star formation, many massive stars live and die in groups. Some leave ringed remnants, others leave diffuse shells. The proportion of each type hints at how often stars follow different evolutionary paths. In that way, one structured remnant does more than tell a single story. It helps calibrate an entire set of stories about how often equatorial rings form, how frequently tilted flows occur, and how commonly explosions reach deep layers of the core. On even larger scales, the remnant contributes to the gradual enrichment of the dwarf galaxy. The mass of heavy elements it carries outward is small compared with the total gas mass of the galaxy, yet locally significant. Regions that lie downwind of the expanding bubble may eventually contain higher concentrations of oxygen, silicon, and iron than regions elsewhere. Over millions of years, those enriched areas can host new clouds, new rings of gas, and new generations of stars. At that stage, the detailed shape of the present rings will long have faded, but the imprinted abundance pattern will still trace back to their earlier presence. From this viewpoint, the remnant becomes part of a chain that stretches from one star's collapse to the chemical makeup of future stellar systems. In this late chapter of the current evolution, the triple ring system and the lobes remain crisp enough to read like a text whose ink has not yet faded. As centuries pass, edges will soften, and contrasts will decrease, yet the remnant will continue to grow slow and mix with the surrounding medium. The next stage will see the rings gradually dismantled and folded into a wider, smoother shell, while the memory of their precise geometry persists in the distribution of energy and elements that continues to expand through the quiet gas of the host galaxy. Far beyond the bright waste of the inner ring, the expanding shell now begins to press more firmly on the quiet gas of the wider dwarf galaxy. That pressure does not carve a single dramatic cavity at once. Instead, it thickens and bends the surrounding medium in stages like a slow breeze reshaping a bank of mist. The leading edge of the shell is no longer a razor-thin blast. It has broadened into a region of enhanced pressure where gas from the remnant and ambient gas move together. Inside this region, density rises gently above the background, and temperatures sit at levels that keep the gas ionized and glowing in soft emission. Farther inward, cooler and denser patches follow, marking where material has already radiated away some of its heat. One guiding idea in this landscape is pressure wave. A pressure wave is a moving zone where gas pushes more strongly on its surroundings than in the undisturbed medium. Another is cloud compression, the squeezing of denser patches of interstellar gas when such a wave passes through them. A third is turbulence, the tangled motion that arises as flows shearfold and break into eddies. Together, these processes turn the once sharp explosion into a long period of quiet shaping, where the remnant no longer tears the medium apart but massages it into new forms. A calm visual anchor appears when the shell is imagined as a very gentle tide rolling onto a broad shallow shore. The tide does not arrive as a single towering wave. Instead, each swell lifts and lowers the water level by a modest amount, shifting sand in thin layers and carving subtle patterns of ridges and hollows. In the remnant, the shell is the swell and the surrounding gas is the sand. Where the gas is denser, the tide's pressure digs slightly deeper and leaves behind compressed ridges of material. Where the gas is thinner, the swell passes with less effect and only faint ripples remain. On small scales, individual clouds a few light years across feel this pressure as a slow squeeze on one side. Over thousands of years, a cloud of that size might see its outer layer thicken into a denser skin, while its interior gains small internal motions. At a radius of about 20 light-years from the centre, the shell may have swept up enough mass to weigh as much as several suns in total gas. In everyday terms, it is as if a sphere carrying several suns of material were inflated to a size that, if shrunk to the scale of a city, would still be only a single gentle dome within many city blocks of surrounding space. The number is modest compared with the galaxy, yet concentrated enough to matter for local structure. A clear limit of observation lies in the span of time available to follow these changes directly. Only a few decades of detailed monitoring capture the early expansion, while the shell's full life will unfold over tens or hundreds of thousands of years. Signals available from the present phase therefore show only a thin slice of its behaviour. Later stages must be inferred from this brief record combined with knowledge of older remnants in other regions. Spatial sensitivity also plays a role. The shell's outermost reaches blend gradually into the background and the smallest ripples in density fall below detectability. The gentle tide can be traced only where its effect is strong enough to stand above the natural irregularities of the surrounding gas. In this regime, pressure waves and cloud compression deliver their most important payoff in how they rearrange the potential sites for future structure. Where the shell passes through a slightly denser filament, it can raise the local density by a factor of a few. That factor may not sound extreme yet. It can move a patch of gas from a state where self-gravity is too weak to gather it into new clumps, into one where collapse becomes easier over long spans. In other words, the shell does not create new clouds from nothing. It nudges existing ones a little closer to conditions where they might later condense. On larger scales, the shell's motion stirs the ambient medium into broader flows. Gas ahead of the front feels a slight push and begins to drift outward. Gas behind it circulates and forms eddies where denser knots from the ring and interior plumes plough through the environment. Turbulence in these regions breaks large coherent flows into smaller swirls, each with its own local density enhancements and deficits. Over time, this cascade helps spread the heavy elements forged in the original star more evenly through a volume hundreds of light-years across. It also seeds a spectrum of density fluctuations that may influence where future clouds form. Magnetic fields frozen into the ionized gas bend and drape around the moving shell. Field lines that once ran more straight now curve and fold following the flow of the disturbed medium. These curves act like guide rails for charged particles, directing some of them along extended paths away from the remnant. In that way, the shell not only moves mass, but also restructures how energy and charged particles thread through the host galaxy's gas. The gentle tide metaphor remains useful here. As each swell moves in Sangreyn's shift and small channels form that direct water along new routes. When the tide recedes, those channels remain and affect how the next swell behaves. In the remnant, the shell's passage rearranges density and field structure. Even after its direct influence fades, the new arrangement influences how later flows and waves move. The scale shift from the immediate vicinity of the ring to this broader region is large. Close-in structures are measured in light months and light years. Farther out, the disturbed volume stretches across tens of light years. On even larger scales, this entire zone occupies only a small fraction of a single spiral arm fragment in the dwarf galaxy. Yet the same event that collapsed a core tens of kilometers wide now leaves marks that reach across all these distances. In the quiet centuries and millennia ahead, the shell will keep slowing and thinning. Eventually, its pressure excess will fall below that of random motions in the surrounding medium. At that point, the tide will have spent its strength. The boundary between remnant and environment will soften until it no longer stands out as a separate structure. What will endure is the slightly altered pattern of density, temperature, composition, and field shape that the shell leaves behind. Those lasting patterns ensure that the death of this single star becomes part of the long, intricate preparation of space for whatever clouds rings, and stars may one day arise from the same region of the dwarf galaxy. Far from the remnant, the larger dwarf galaxy carries on its slow rotation around the center of its parent system. Within that wider motion, the triple ring structure is only one delicate mark. Yet the energy and elements it spreads reach distances that link it to gas clouds that never felt the original star's light directly. Over time, the remnant becomes part of a chain that ties together old stars, diffuse gas, and future generations of stellar systems. The guiding ideas here are feedback enrichment and a memory. Feedback describes how stellar deaths return energy and motion to their surroundings. Enrichment describes how newly forged heavy elements mix into previously simpler gas. Memory describes how these changes leave long-lasting patterns in the structure and composition of the galaxy. Together, they show that the remnant is not an isolated curiosity, but one moving piece in a slow conversation between stars and the medium that hosts them. A calm visual anchor appears when this system is imagined as a wide plain of snow under dim sky. In one small area, a heavy object strikes the surface and throws up a ring-shaped ridge with faint arcs beyond it. For a while, that pattern stands out sharp and bright. As wind and time pass, edges soften, and fresh snow falls, yet the material pushed aside by the impact still lies where it was moved. Even when the shape is no longer easy to follow, the distribution of snow grains remembers that an event once reshaped the plane. In the remnant, the rings and lobes are the ridge pattern. The enrichment and stirred gas they leave behind are like the redistributed snow that persists beneath later layers. On smaller scales, heavy elements from the remnant gradually drift into nearby filaments of gas. Some of these filaments coil around cavities carved by other ancient explosions. Others run through calmer zones that have not yet hosted major shocks. Within each filament, atoms of oxygen, silicon, and iron spread out and mix with hydrogen and helium. Over hundreds of thousands of years, cooling in denser segments of these filaments allows molecules and dust grains to form. The presence of heavier elements changes how efficiently these grains radiate heat and how quickly gas can fragment into smaller clumps. A single approximate number suggests the reach of this process. Over a span of 10 million years, material from the remnant can drift and mix across a region dozens of light years wide. Compared with the thickness of a galactic disk, that region is still small. Compared with the scale of a single young stellar group, it is large enough to include many potential sites of future collapse. In that way, the products of one stellar death can become part of the raw material for several later stellar births. There is a limit of observation in this far-reaching chapter. No distant signal can follow individual atoms from the remnant into future clouds and stars. The mixing unfolds over times far longer than any current monitoring sequence. Instead, understanding of this stage relies on comparing regions with different histories of explosions and looking for broad trends in composition and structure. Those trends show that areas with more past remnants tend to display higher fractions of heavy elements and more complex dust populations. From that pattern, it is inferred that each event like this one contributes a small but real step toward the gradual chemical maturation of its host galaxy. In that wider context, the shape of the rings carries a subtle extra meaning. The equatorial band and tilted outer arcs show that the progenitor did not simply blow away mass evenly in all directions. It preferred a waste, then favoured certain latitudes. This anisotropy means that heavy elements are not injected uniformly into the surrounding gas. Some directions receive more of certain nuclei, while other directions receive less. Over large scales and long times, contributions from many such events smooth out, yet local differences persist for a while. These local patches of slightly different composition may influence the cooling efficiency and grain formation in specific clouds, nudging them toward different evolutionary outcomes. On the smallest scales, conditions inside any new collapsing cloud depend mainly on its immediate density and temperature. On intermediate scales, those conditions reflect how many past shocks have passed through and how much enriched material they delivered. On the largest scales, the overall metallicity of the dwarf galaxy increases slowly as each generation of massive stars lives and dies. This nested set of influences ties the compact remnant only a few light-years wide today to the eventual makeup of stars that may form hundreds of light-years away in the distant future. A gentle payoff emerges when the chain of causes is traced. The collapse of a core that lasted less than 1 second leads to an explosion that reshaped gas over decades. That reshaping seeds density variations and enrichment that matter over millions of years. Later, when new stars condense in regions affected by these changes, their planets, if any form, inherit different blends of elements than they would have without the old remnant's contribution. The story of those future systems silently includes the triple ring structure as one of its early characters, even if no trace of the visible ring survives. A clear limit of intuition appears when thinking about such long connections in time. Human-scaled experience favours chains of cause and effect that resolve within days or years. Here, links between events stretch across spans where entire civilizations could rise and fade before the chain completes. To bridge that gap, it helps to think in terms of simple repeated steps. Each explosion moves matter and energy a little, enriches gas a little, and stirs structure a little. Many such steps, combined over long periods, add up to large differences. The remnant around the former star now sits at one step in this sequence. In the quiet ages ahead, its rings will soften, its shell will thin, and eventually its outline will fade into the background of the host galaxy. The compact object at its centre will continue to exist as a small dense point, perhaps still spinning, perhaps already slowed. Gas once organised into bright arcs and sharp edges will have dissolved into the general flow. Yet the elements it carries and the patterns it impressed on the surrounding medium will remain folded into the galaxy's fabric. In that sense, the remnant completes a full circle from concentrated core to diffuse influence from a single star's interior to a contribution spread across many light-years of space. As the rings continue their slow fading, the remnant settles into its longest chapter. That chapter is less about bright change and more about quiet persistence across cosmic scales. The once violent event becomes a stable feature of its dwarf galaxy, a shaped volume of gas, and a compact core that simply endures. While shocks weaken and edges blur, the structure still marks the place where one massive star ended and left permanent fingerprints on its surroundings. The guiding ideas now are longevity, background, and imprint. Longevity describes how long the remnant remains a distinct structure compared with the brief life of the progenitor star. Background describes how the remnant gradually merges into the general glow and motion of the host galaxy. Imprint describes the marks that remain even after the structure itself can no longer be separated from its environment. Together, these ideas show how a single event shifts from a dramatic episode into a quiet, almost invisible influence spread over enormous distances. A calm visual anchor appears when this long stage is imagined as a series of rings inside a very old piece of wood. In a cross-section of a tree trunk, rings near the center record seasons that ended long ago, while the outer layers carry more recent growth. From a distance, the surface looks like a smooth disk of brown and gold, yet up close each ring marks a distinct cycle. In the remnant, the bright inner ring, the outer arcs and the expanding shell act like such growth rings carved into interstellar gas. As expansion proceeds, these rings soften, merge, and finally blend into a nearly uniform texture, but the history that laid them down remains encoded in density and composition. One approximate number anchors the scale of this lasting presence. The remnant lies about 160,000 light-years from the centre of the larger galaxy system that hosts its dwarf companion. If that distance were shrunk so that the gap between galaxies spanned the width of a continent, the entire triple ring structure would be smaller than a single grain of sand resting on that landscape. This contrast highlights a deep-scale shift. A structure only a few light-years wide can still matter inside a system hundreds of thousands of light-years across, because the processes it represents repeat many times throughout that vast space. On shorter timescales, the remnant's evolution slows to a near standstill. Centuries pass with only modest changes in radius or brightness distributions. The inner ring gradually erodes into a faint, ragged band. The outer rings lose their clear arcs and become mild enhancements embedded in a broader haze. The lobes inflate further, then lose contrast as they trade energy with the surrounding gas. Eventually, the remnant's edge no longer appears as a sharp boundary at all, only as a gentle gradient where density and temperature still differ slightly from the undisturbed medium. During this phase, the compact object at the centre continues its quiet existence. If it remains a neutron star, it turns in the darkness with immense density and strong gravity wrapped in the diffuse fog of the ever-thinning ejecta. Its light, if any, becomes only a small part of the region's overall glow. The main signature of the event has shifted from vivid rings and flaring shocks to subtler patterns in composition and motion. A clear limit of observation applies strongly here. The slower the evolution becomes, the harder it is to notice from one epoch to the next. Differences that matter physically may require centuries or millennia to accumulate. Any finite sequence of recorded signals samples only a tiny fraction of that future. Resolution also becomes a barrier because as edges soften and contrasts fall, the remnant's outer parts become impossible to separate cleanly from the background. At that stage, only the inner zones or particularly dense knots remain identifiable, while the majority of the volume has effectively joined the general interstellar medium. Even with these limits, the long-lived imprint retains a simple, stable pattern. Inside some radius, gas is slightly more enriched with heavy elements than gas farther out. Within that enriched zone, small variations in density and temperature follow the paths once carved by Schick's plumes and mixing layers. Magnetic fields shaped earlier by the expanding shell continue to arch and curve through the region. On large scales, these differences may be modest. On local scales, they can affect how future clouds cool where small clumps condense, and how filaments align. The old tree trunk analogy remains useful. Even when the trunk weathers and its surface cracks, the spacing and thickness of its rings still reflect past conditions. Narrow rings point to slower growth, wider rings to more favourable periods. In the same way, the radial profile of enriched gas, the subtle remnants of the equatorial band, and the faded arcs of the outer rings all encode information about the progenitor's wind's rotation and final collapse. Reading that information in full would require perfect knowledge of gas motions and composition, which is beyond any practical reach, but the pattern exists regardless of whether it is ever fully decoded. The remnant's place in the dwarf galaxy's wider structure also shifts. Early on, it stands out as a bright knot within one section of a gaseous arm. Later, it becomes one of many overlapping bubble shells and irregular patches that together form a textured background. Some neighbouring regions may host their own remnants, creating a network of partially merged cavities and enriched zones. Over tens of millions of years, this network stretches and shears as the dwarf galaxy orbits its larger companion, turning distinct patterns into long streaks and arcs of altered gas. A gentle payoff emerges when the full chain of scales is viewed together. A core only tens of kilometres across collapses in less than 1 second. Over minutes and hours that collapse drives shocks that shape structures a few light hours wide. Over years and decades, those structures grow to span light months and light years, carving rings and lobes. Over centuries and millennia, the remnant's shell expands, slows and merges into a region tens of light years across. Over millions of years, the marks it leaves influence the birthplaces of new stars within its dwarf galaxy. The original star has long vanished, yet its final act echoes across distances and times that exceed its own lifetime by many orders of magnitude. In this late chapter, the triple ring remnant has become both small and large at once. Small because its bright features occupy only a tiny portion of the host galaxy and fade into the general haze. Large because the energy and elements it released continue to participate in motions and structures far beyond the original blast. The quiet interior, the softened rings, and the barely distinct shell form a stable, restful, stunning scene. In the final part of this story, attention can drift from specific boundaries and numbers to the simple fact that such remnants exist at all, scattered through the dark, each one a calm marker of a star that once burned and then carefully handed its matter back to the wider cosmos. In the quiet present, the triple ring remnant now rests as one more gentle pattern in a deep dark galaxy. Its brightest days have passed, yet its shape still holds a calm story about how matter moves from one form to another. The once blinding flash has softened into arcs, knots, and a faint shell, each carrying a memory of the forces that shaped them. The core has finished its violent rearrangement and now exists as a compact, stable object that does little more than curve space in its vicinity. Around it, the inner ring still traces a narrow waste where earlier winds met and piled up. Farther out, the outer rings keep their tilted arcs like careful marks that show the angles of the old stellar envelope. The guiding ideas in this closing chapter are continuity, return, and rest. Continuity means that the processes seen here are not unique, but part of a pattern repeated wherever massive stars live and die. Return means that the elements forged in the core do not vanish, but rejoin the diffuse gas between stars. Rest means that after shocks, turbulence, and rapid change, the remnant enters a long era of slow, almost imperceptible evolution. Together, these ideas turn the detailed structures of this one event into a soft, reassuring example of how the cosmos keeps reusing its material. A calm visual anchor appears when the region is compared to a large dim room, where a single lamp once burned strongly. Long after the flame has faded, a faint glow still lingers on nearby walls, and dust motes drift slowly through a pale beam that enters from far away. In the remnant, the central flash is gone, but delicate arcs still hold light and fine structures still float in the surrounding medium. The gas is not uniform. It carries gradients in density and composition with slightly heavier material tracing paths carved by earlier waves. On small scales, clumps the size of a few light days drift and slowly mix. On intermediate scales, the lobes still outline a broader peanut-shaped volume filled with stirred gas. On the larger scales, the entire remnant remains only a small patch within its dwarf galaxy, which itself orbits inside a larger system. This layered arrangement of scales ensures that no single distance fully describes the structure. At arm's length on a cosmic map, the remnant is a dot. Up close, it is an intricate landscape of rig folds and gradients. One simple number helps anchor this view. Over the next 10 million years, material from the remnant can spread through a region spanning tens of light years. In everyday terms, that is like watching smoke from a single small fire gradually fill a wide valley, seeping into every hollow and around every ridge. The fire is brief. The distribution it creates endures much longer. In a similar way, the explosion of the original star was short, but the rearrangement of gas and elements continues across time far beyond the star's life. There is a clear limit of observation when considering such spans. No direct record can follow the remnant from bright arcs, now to the clouds and stars that may one day form from its debris. Only snapshots at different stages in different regions can be compared and interpreted as parts of the same type of story. This limit is not a flaw in the cosmos. It is simply a reminder that awareness occupies a narrow window in time, while the processes described here unfold across intervals so long that most structures change only slightly within any brief watching period. Even with that restriction, the overall direction is simple. Energy that was once locked in the core has been shared with the surrounding gas. Elements that were once fused in dense layers now drift in thin clouds. Boundaries that were once sharp have become gentle transitions between zones of slightly different density and temperature. The triple ring remnant illustrates this direction in a particularly graceful way. The inner ring shows where the progenitor shaped its environment with steady winds. The outer rings show where earlier mass loss formed tilted shells. The lobes and shell show how the explosion used those prepared structures as guides. Finally, the broader mixed volume shows how everything tends toward a smoother, quieter state. A different analogy can frame this final stage. Consider a wide garden of dark soil scattered with seeds. A single stone is dropped into the ground at one location, sending a soft shock through nearby earth and rearranging grains in a pattern that slowly fades. Later plants growing in that patch may differ slightly from plants elsewhere, because the soil there was compacted and enriched in a specific way. The stone is gone from view, yet its influence persists in subtle textures. In the remnant, the massive star is gone, but its last act has tilted probabilities in a small part of its galaxy, making certain future configurations of gas and dust more likely than others. On a still larger scale, this story merges with those of many other remnants scattered through the wider system. Each one followed its own exact sequence of winds, collapse, and shock. Each one carved rings, shells, or filaments in its own environment. Seen together, they form a loose overlapping network of altered regions, each quietly preparing gas for different paths of cooling and condensation. The triple ring structure is simply one of the most clearly drawn and neat example of how a star's long preparation and brief death can shape space in stages. In the far future, long after its arcs have fully blended into the surrounding medium, nothing in the sky will obviously mark the site of this specific event. Gas enriched here will have mixed into new clouds. Some of those clouds may collapse into young clusters. Some of those clusters may form planets rich in the same elements now glowing in the remnant's knots. The connection from present structure to those distant outcomes is not direct, yet it is real in the quiet language of mass, energy, and time. For now, the remnant remains what it is at this moment: a compact core at the centre, 3 main rings of Kess arranged in a tilted pattern, lobes and shells extending outward in a gentle fading glow. Beyond them, the calm disk of a dwarf galaxy, circle upon circle, turning slowly in a wider sea of dark space. The journey of this single star has run its course, leaving only ordered, light-enriched gas and a softly marked volume behind. In that stable scene, motion continues, but urgency has drained away, and the cosmos around SN 1987A's rings settles into a long, quiet breath.